Hi everyone, this is Kalyan Kumar and welcome to Chemistry Tutorials, your one-stop channel for a variety of chemistry videos covering all parts of chemistry, physical, organic and inorganic. Now we have been doing the lesson General Organic Chemistry for a while now, and in the last episode I posted various types of reactive intermediates that very often occur in chemical reactions. With that, we have technically finished the entire theory of General Organic Chemistry. We started with various hybridizations of carbon. We went through inductive effects, we went through resonance effect and the various situations when resonance occurs. We talked about aromaticity, and then we talked about hyperconjugation, then we talked about temporary effect like electromeric effect. Then we looked at the difference between transition states and intermediates, and then we talked about reactive intermediates in the last episode. So from now on, we are going to look at the application of whatever we have learned. We're going to look at the application of inductive effect. We're going to look at the application of resonance effect, hyperconjugation in various properties of a molecule. Properties namely stability of an ion, stability of a molecule, bond strength, acidic strength, basic strength. So we're going to look into all aspects of the molecule using these effects. So this one is part 7 of 13 and this is titled Stability of Intermediates, and in this one we are going to look at carbocation. And the way this is going to go is I'm going to show you some molecules and you are going to draw those molecules, pause the video, draw all the molecules. I'll first show you all the molecules that I'm going to compare, and then I would want you to use your own concepts, the concepts that you've understood, and use them and figure out the stability of each of these, stability order, decreasing order, increasing order, whichever way. I'm going to do generally decreasing order. Then you look into the video and figure out whether what you have thought was correct or not, and also the reasons. The reasons are the most important ones here. Now at the outset, let me also tell you that not everything will go as you predict, because that is the very nature of the word called prediction. It implies that you can be right, you can be wrong also. So you must ensure that you do your best in figuring out, and as you see new things happening, certain things which are exceptions, you will learn those exceptions as time goes by, and you will use those knowledge, the knowledge gained from these exercises, in predicting in an exam the stability or the acidic strength or the basic strength of two different molecules. So let's begin with this episode. This is part 7 of 13, Stability of Intermediates, and the first one we are going to do is carbocation. So as you can notice, I'm going to give you some molecules now. Now first of all, tell me, what does it mean if I draw a line like this? What does it mean now? Now obviously you may think it's a line, but remember, if I were to draw this, you are not going to say it's a hexagon with 3 alternate lines. You are going to call it benzene, right? Because by default you're assuming each of these points is a carbon. Bonds shown are carbon-carbon bonds, and bonds which are not shown, which are implicit, are the carbon-hydrogen bonds. Similarly, by that logic, this is CH3, CH3, that is, this is ethane. So the first ion that is coming your way is this one. So what do you think this is? This is obviously CH2 positive, CH3. So instead of writing this, I'm just writing like this. So figure out what is this. This is obviously CH3, CH2 plus CH3. What is this? This is CH3 3 times and C positive. Now this one is called a tertiary carbocation. Tertiary carbocation, because this carbon, which is a carbocation, is attached to 3 carbons. This guy is known as a secondary carbocation. Tertiary is also represented as 3 degree. This is called a secondary carbocation, represented as 2 degree. And this is CH3, CH2 positive, only 1 carbon it is attached to. So this is called a primary carbocation or a 1 degree carbocation. Now, having said that, you must also understand that if I say tertiary carbocation, it does not necessarily mean 3 CH3s attached to 1 carbon. It could mean only that 3 carbons are attached to 1 carbon. what is attached to those carbons is not implied in tertiary carbocation term. So it could be attached to hydrogens, it could be attached to fluorine, it could be attached to almost anything. So tertiary carbocation does not necessarily imply CH3 thrice C+. It implies only that the C+ is attached to 3 carbon atoms. The next one is this one. So what do you think this is? CH2 positive F. What do you think this is? CH3 CH2 plus F. And what do you think this is? CH2 positive CH2 F. So we are going to compare all these 6 carbocations. We'll go one by one. And now I want you to pause the video. Now that you've seen all the carbocations, I want you to pause the video and then play it back once you have been able to figure out the order of stability and the reasons that you consider them to be in that particular order. So now that you must have tried this on your own, let's check out let's start with 1 and 2. Which do you think is more stable, 1 or 2? And the answer is 2 is more stable than 1. And why is it so? That's because 2 has one additional CH3. This has got only one CH3. Now CH3 by definition shows plus I effect. But that is not the primary reason for 2 to be more than 1. The main reason is it has got 6 alpha hydrogens to hyperconjugate, whereas 1 has only 3 alpha hydrogens to hyperconjugate. Therefore, 2 CH3s will give you a hyperconjugation of 6 hydrogens. This will give you a hyperconjugation of 3 hydrogens. So therefore, apart from having one additional inductive effect, it also has 3 additional hyperconjugative effects. So in this case, the iron 2 is more stable than iron 1, and this is the reason. 2 is more stable than 1 because 2 has 2 plus I effects and 6 plus H, while 1 has only 1 plus I and 3 plus H. Now at this point of time, I would like to mention that if you're ever asked this question in a subjective kind of an exam, where you have to give a reason, it is very important for you to write hyperconjugation most importantly. Even if you miss out inductive, it's okay. But if you miss out hyperconjugation and write only inductive, it will be wrong. Moreover, when you are writing subjective answers, always underline the keywords. If you're talking about inductive and hyperconjugation, remember nobody has that much amount of time to read each and every answer, decode your handwriting, which most of the time is like a puzzle in itself. Therefore, to figure out what you have written and then try to understand it and make sense of it. So it is always better that whenever you write an explanation for something like this, you always underline inductive, you always underline hyperconjugation. That way the examiner knows that this guy knows the basic facts, the rest is only English, and that definitely is not going to matter that much. So let's compare 3 and 2. So what do you think 3 and 2? I think going by the same logic, you can very clearly say 3 is more stable than 2. That's because it has got one additional CH3. And one additional CH3 means 3 additional hyperconjugation. Total hyperconjugation is 9 in 3, 6 in 2. And one additional inductive, of course, in 3. So the reason is pretty simple. 3 is more stable than 2 because 3 has 3 plus I effects and 9 plus H effects, while 2 has only 2 plus I effect and 6 plus H effects. Now at the same time, you must also understand that since 3 is more than 2 and 2 is more than 1, one may conclude tertiary carbocation is more stable than secondary and secondary is more stable than primary. But that is not the case. It is only in this particular type of tertiary and secondary and primary that the order is like this. If the carbons were attached to fluorine instead of hydrogen, the order would have been the other way around, because fluorine is electron withdrawing. There will be first of all no hyperconjugation, only inductive, and that too will be minus I. So when you are trying to pull electrons from a carbon which is already plus, the positive charge on the carbon is going to increase more, and therefore it is going to be more unstable. Therefore, please do not make this mistake of always assuming tertiary is more than secondary, secondary is more than primary. It is only if tertiary, secondary, primary are the ones that I have shown to you. And tertiary by default does not mean this particular ion that I have shown you. Alright, now I want you to compare 4 and 1. Molecule 4 with molecule 1 because 1 is the least among 1, 2, 3. So I want to know where does 4 stand. So what do you think? Now one might say that 4 will be less than 1 because of minus I effect of fluorine. Well, but you must also look at one thing. Just look at the fluorine now. Can you see it as a lone pair? And lone pair positive charge are conjugated. So it will do resonance and thereby get one more structure, this one. Now in most of the times when I ask my students which structure is more stable, by default they'll say the lower one. Because here the carbon has plus and here the fluorine has plus. Fluorine is more electronegative. Again wrong. It is this which is more stable because here the octet of carbon is complete. Octet of fluorine was complete here as well and here as well. Whereas in this case the carbon's octet is not complete, here the carbon's octet is complete. And if you remember resonance, where I gave you the stability order of resonating structures having a single positive charge, the first option, the first condition was the structure in which octet of all atoms is complete is most stable. It's only once this is done that you look at where the charge is located, whether it is an electropositive or electronegative element. But otherwise, it has to be taken for granted that it is the octet completion which has to be seen first. So here the octet of carbon is complete and therefore the upper structure should be more stable. So now with this new information, what do you think? Is 4 less than 1 or more than 1? Now, it is still less than 1. Now again, you would wonder as to why I'm doing this. I mean, you already thought perhaps 4 was less than 1. Then I forced you to believe 4 is more than 1 by giving you all those reasons. And again 4 is less than 1. It is because you must know that in spite of the fact that it has a lot of effects that make it more stable than 1, it is still less than 1. And now let's see the reason. The reason is pretty simple. For halogens, the inductive effect always is greater than their resonance effect. 4 is less stable than 1 even though 4 shows lone pair double bond resonance, due to which octet of carbon gets completed without compromising the octet of fluorine. This is because, as in all halogens, their minus I effect dominates the plus R effect. The resultant is an electron withdrawing effect. This destabilizes the carbonium ion 4 compared to 1. So what we are basically saying is that for fluorine, the reason inductive effect is greater than resonance effect is because its minus I is the greatest. It is the most electronegative element. So its minus I effect is the greatest. Therefore, its inductive effect is so high that it overpasses the resonance effect. On the other hand, when it comes to chlorine and other halogens, the reason the inductive supersedes the resonance effect is because the resonance is bad. The orbital in which these lone pair exist are 3p, whereas the carbon to which they are trying to resonate with has orbital which are 2p. 2p and 3p don't form good bond. So for chlorine, the resonance effect itself is lower and its inductive effect is okay. So because the resonance goes down, it becomes less than inductive. So please understand that for fluorine, chlorine and other halogens, the reasons are different. For fluorine, the inductive is so high, it overpowers resonance. For other halogens, the resonance is so bad that it goes below inductive. Though the net effect is same, minus I. It is ultimately electron withdrawing by inductive which wins, but the reasons are different. Alright, so let's look at 5 now. So what do you think about 5 and 4? Now in 5, you got fluorine attached to C plus, CH2 plus, CH plus, and there is a CH3 here. So what do you think between 5 and 4? And I'm sure you'll be able to understand that in 5, this part is same as this part. So this part is same as this part. C plus attached to fluorine. But 5 additionally has one CH3. So will the CH3 help in stability or not? It will definitely help in stability because it will offer 3 more hyperconjugative structures and 1 plus I effect. Therefore 5 will be definitely more than 4. Now coming to the question of 5 versus 1. Now again, this part in 1 and this part in 5 are common. Only thing is it has one additional F. And as we've already seen in 4, having an F is going to help you by resonance, not help the stability by minus I, but the winner is minus I. So the net effect of fluorine is withdrawing effect. So since it is net withdrawing effect, ultimately 5 will become less than 1. So 5 is less than 1, greater than 4, and it is this. And 5 is more stable than 4 because it has 1 additional plus I effect and 3 additional plus H effects due to a methyl group, and it is less stable than 1 because the net effect of the presence of fluorine in 5 is electron withdrawing effect, which destabilizes the carbocation 5 as compared to 1. So now let's check out the last one, 6 and 5. What do you think? Now, or rather 6 and 4. Let's look at 6 and 4. Now in 6 and 4, it's a little bit complicated. There are some reasons that will point to 6 being more stable, some reasons that will point to 4 being more stable. So let's look at that one. Now here in 4, you've already seen minus I dominates. And one may feel that here the fluorine is a little further away from this carbocation. It's not right attached to it. It is one removed from it. There's a carbon here. Moreover, this guy has 2 hydrogens. So one may feel that 2 hyperconjugation here, less inductive here, should make 6 more stable than 4. Let's look at 6. Oh God, it's less than 4 now. It should have been more than 4, right? Because it has got less inductive, fluorine being further away, 2 hyperconjugation. So what happened? Well, the logic is this. Fluorine has more minus I here than here, accepted. But a large chunk of its minus I is being reduced by the plus R effect. Because remember, in the case of fluorine, the plus R effect is very good. In fluorine, the orbital used to house the lone pair is 2p, and carbon is also 2p, and 2p bonds are perfect. Therefore, the resonance effect of fluorine is definitely very good. But its inductive is greater, that's why it supersedes. But one can say that the minus I and the plus R may not be that different in value. Though we are trying to predict things qualitatively, we can't do anything quantitatively here. But one can say with reasonable surety that the resonance effect is very high, though inductive dominates, there could be only a small difference between the two. So let's say, for the sake of making you understand, let's say the inductive was minus 20 in some units and the resonance was plus 18 in some units. So the net effect is minus 2, withdrawing. Whereas here the fluorine being removed from the carbocation, its inductive is less than minus 20. Let's make it minus 10. Let's reduce it by almost half, which is not the case, but let's do it. And let's say there are 2 hyperconjugations, which would be definitely not in the region of resonance. Let's say plus 5 perhaps. So what is the net effect? Minus 5. Can you see here the withdrawing is more than here? Now, you may argue that I have made up these numbers, but I may have made up these numbers, but the fact remains that 6 is less than 4. I have not just made up the facts. Facts are there. Only the numbers that I am using are perhaps imaginary, but then they do explain this fact. And the actual numbers would be somewhat similar to this. So the reason 6 is less than 4, because in 6, only the minus I effect of fluorine is operative, while in 4 a major chunk of minus I is cancelled by plus R. So the net withdrawing in 4 is less. Because what you need to notice is, in 6 there is no resonance at all. There is no resonance effect. Here at least you have some resonance effect to cancel the minus I. Here you have only 2 hyperconjugative structures which are as it is weak. Therefore, 6 is less than 4. So now I'm going to give you another set of ions, carbocations again. And you got to figure out the stability using the same rule. I'll give you all the ions first, pause the video, do it on your own, come back and then play it back. So the next one is this guy, tertiary. Now this next ion is called benzylic. This carbon is called benzylic carbocation. The next is also benzylic, but it is substituted benzylic. The benzene has a substitution there. And the next one is substituted with halogen. The next one is substituted with nitro. And the next one, number 6, is called allylic. Remember, these two carbons are called vinylic as their sp2, and this guy sp3 attached to the sp2 is called allylic. This is allylic carbocation. All right. So now look at the stability now. 2 and 1. Which one do you think is more stable? Now obviously 1 has 9 hyperconjugation going for it and 3 inductive. Whereas 2, let's look at 2 now. This is molecule 2, ion 2. Can you see this positive charge is conjugated with this double bond? So there will be resonance. It will give you this, which will again undergo resonance. Will give you this, again resonance. You get this. Now I'm not drawing the next structure because the plus will again come here. But remember, in the next structure, though the plus will come on the same carbon, it should be treated as a separate structure because the position of double bonds has changed. So this structure is different from this structure. But since the positive charge has come out of the same carbon, so it's not going to help me in explaining the stability of this. So this benzylic carbocation has 4 resonating structures. And let's see 4 resonance versus 9 hyperconjugation and 2 inductive. How does it check out? So 2 is less than 1. 2 is less than 1. Now you may feel this is unfair, and it is unfair because it is not possible to compare these two. They are totally different. You got 9 hyperconjugation on one side and 4 resonating structures on the other side, and you won't be able to figure out. You can only say one resonance is greater than one hyperconjugation, but you can't figure out how many hyperconjugation is equal to how many resonance. And in doing this, let me also mention there are some people, some instructors, I'm sorry to say, they have this habit of looking at this and then trying to make some kind of formula saying so much of hyperconjugation is equal to so much of resonance. That is total crap. It doesn't work like that, because it is unquantified. It is just that they look at this particular stability order and using this they figure out, okay, this is greater than this, so many of this is greater than so many of that. Nothing of this is given in any kind of book. It is self-made and it doesn't stand to reason or stand to any kind of scrutiny. So please do not ever accept those kind of bogus explanations. The fact of the matter is, you cannot compare them. One is tertiary, one is benzylic, hyperconjugation, resonance. You can't compare them because there are 9 of this and 4 of that. So what might be able to satisfy you is the fact that in the case of benzylic carbocation, since the pi bond is going outside the ring to resonate with a positive charge, it ends up losing its aromatic character in that process. And aromatic character breeds stability. So in order to maintain stability, it tends to remain as an aromatic ring. But of course, by delocalizing, it again gets stability. So it will only delocalize the pi electrons of an aromatic ring as much as so that the stability gained is more than the stability lost due to loss of aromatic character. By delocalizing the charge, you are getting more stable. And by giving the electron outside, you are delocalizing it, but at the same time losing the aromatic character, you are getting instability. So whichever is greater will happen. So it is possible that the resonance in 2 may not be to that extent as it might have been had the ring not been aromatic. So because of a loss of aromatic character, it would tend to resonate less. And probably that is one of the reasons why it is less than 1. So 1 is more stable than 2 because 3 plus I effects and 9 plus H effect in 1 must be outweighing the plus R effect of benzene in 2. The fact that benzene loses its aromatic character in resonance is perhaps an influencing reason. Now let's look at 3 and 2. So what do you think between 3 and 2? Let's check out again. This is 2, right? Now this is 3. You have got OMe in all of them, and I hope you understand what is Me. Me is methyl group, CH3. Now here you will notice there is a lone pair here. Sorry, there's a positive charge here, and the O has lone pair. And this lone pair is conjugated with a positive charge. It will undergo resonance, and in doing that, it will create one more resonating structure where the octet of all atoms is complete. Octet of carbon is complete. So it's a very high contributing structure. So this has created more stability for the benzylic type of carbocation. And therefore, 3 must definitely be more than 2. But whether is it going to be more than 1 or not is difficult to say. But if you can assume that 1 and 2 are not that different from each other, then one will be able to understand that since 3 is quite much higher than 2, there's a good possibility it might be much higher than 1 also. So this is 3. 3 is more stable than 2 because it has 4th resonating structure in which the octet of all atoms is complete. It is also more stable than 1 as this could be a dominating reason. Let's look at 4. 4 and 2. What do you think? Now 4 also has a lone pair. But you already know that when the plus comes here, it will resonate and complete the octet. But in spite of that, for halogens, we know inductive dominates over resonance. For halogens, inductive effect dominates over resonance. So if you have a halogen, it can give and take, it will take more than it gives. So definitely 4 is going to be less than 2. What about 5 and 4? So let's check out 5 now. So this was molecule 3, ion 3. This is the 5th one, nitro. And as you notice here, in this, as it is, nitro is a withdrawing group. So it is going to destabilize carbocation, no doubt. Moreover, there is one resonating structure in which adjacent atoms are positive charge. This carbon is positive, this N is positive. That would make repulsion so great that it will almost make this structure not workable at all. So what happens is that 5 must be much less than 4. And the reason 4 was below 2 is 4 less stable than 2 because minus side effect dominates in halogens. And in 5, you find that one structure is almost not going to work, it's not going to contribute because of the fact that it is highly unstable. So now let's look at molecule or ion number 6 and compare it with 2. I'm comparing it with 2. Now 6 has positive charge conjugated with a double bond. So what will happen is there will be a resonance like this, and this will resonate to give you this guy. 2 equivalent resonating structures. Now 2 has 4 structures. These are the 4 places in which the positive charge goes. 6 has 2 places go. So by sheer number, one would expect 2 to be more than 6. Because 2 has 4 structures, 4 is greater than 2, and one might feel that 4 being more than 2, it would work out. But remember, it's not that easy to figure this out. For the simple reason that here in the last one, you're able to get 2 equivalent structures. There's a positive charge, 0.5 on each of the terminal carbons due to resonance. Whereas in the case of molecule 2, the benzylic one, it is difficult to figure out how much charge the carbon will have because it is getting distributed into 4. So will it be less than 0.5, will it be more than 0.5 is something which is hard to guess. But it so happens that 6, where does it go? Alright, it's less than 2, more than 4 and 5. So perhaps the fact that this has 4 structures seems to have won over the fact that this has only 2 of them. 6 is more stable than 4 and 5 because the resultant effect of in 4 and 5 is minus I, and it is less than 2 because 2 has 4 structures while 6 has only 2. Remember, it could have so happened that if 6 had been more than 2 in terms of stability, then I would have said, both structures contribute equally 50% each. Here there are 4 structures and 2, but 3 of them are the non-aromatic variety. Only one is the aromatic variety. So perhaps the one which is aromatic contributes perhaps 60%, which would make the charge on it 0.6, whereas the charge on the allylic has 0.5, which makes the allylic more stable than the benzylic. So remember, the idea is that you may not be able to predict everything correctly, but if you are able to give the correct reason for a given fact, that is very, very important. That is what you got to learn. Anomalies will come, you cannot predict them. So the idea is that you should be able to give the correct reason if the correct fact is given to you. So let's see the reason for this. 6 is more stable than 4 and 5 because in 4 and 5 minus I effect works. It is less stable than 2 because 2 has 4 structures while 6 has only 2 of them. So that completes this particular video on the stability of carbocation. If required, go ahead and watch it as many times as you want. And if you want to download them, there is one simple method of doing that. You just download a software called 4K Downloader. It's a free software available. You can install it in your computer and go to this particular video on YouTube. Copy the link, paste the link on that 4K downloader. It will automatically download the highest resolution for you. It will give you all the options of all the resolution that you want to download. Depending upon your data, your internet data consumption, you can download videos right from 1080p. The highest resolution will be 1080p up to 240p. So you can download all the different types of files that you want depending upon your need. And that way you will be able to watch these videos offline also. So that's it from my side on this video. If you haven't subscribed to this channel, I encourage you to subscribe to this channel. Consider subscribing if you found this video informative and interesting. At the same time, if you do like the video, don't forget to hit the thumbs up button. Your encouragement is very much required. And once you subscribe, also hit the bell icon on top. That will help you get the notifications of all the videos I upload right on time. With that, this is Kalyan Kumar signing off. Have a great day, goodbye, and thank you for watching.